Hey there, I'm Daniel, and I wanted to go ahead and answer some questions that I get pretty often, and then one particular question that I got on my What is Classical Math video. I don't have a ton of time to make videos these days, unfortunately, so I apologize for the long stretches of time between videos, but I am a teacher, and I teach full-time in addition to working on a PhD in English, which is the other thing I'm doing besides teaching math. So I don't have a ton of time. But that said, I did want to make a quick video just to address some of these questions that I've gotten because I think that they're worth talking about. So I'll begin with the question I got on my What is Classical Math video. I'll read it to you, and then I'll respond. So the question says, I learned a lot from your video. Thank you. I'm curious on your thoughts about the negative consequences of using only European examples of math thinkers and doers. For example, with algebra, our number system being rooted in Persia, are you really providing examples of creativity if you present the European representation of Persian constructions? European representation of Persian constructions. So that's the first part of the question. Which I'll address. So, I think the best way to answer this is to say that there actually was quite a bit of creativity in Europe that was sparked by the arrival of these Arabic texts. So what had happened, right, was that the Greeks had done all this stuff with math, and it had been preserved by the Arabs and extended in some cases by the Arab mathematicians. And so when these things re-entered Europe, in one sense, it was a re-entering of Greek learning, but it had been, of course, preserved and extended by the Arabs. And that's not to downplay their contributions. However, as far as I know, the Arabs and even the Hindus were not as systematic as the Greeks in their approach to math. And so their contributions are real contributions, but they're contributions at a different level. And so compared to the large systemic contributions of the Greeks, the contributions of the Arabs and Hindu mathematicians, as far as I know, were comparatively slight. Now, I might be wrong about that because I genuinely don't know a whole lot about this because none of the writers I've read have really emphasized the Arabian, Persian, or Indian achievements in math. So I'm just telling you what I know. So here's the second part to that question. Also, I'm not very familiar with classical education. When you describe literature and Latin instruction, is it accurate to say that you de-emphasize students' opportunities to write and create their own work? Is it not a detriment to not provide opportunities for students to be problem solvers themselves, or to construct their own theorems or proofs? I know you said math should not be considered a mental exercise. However, when would students have the opportunity to become critical thinkers and problem solvers and creative with mathematics? Maybe I'm misunderstanding. I would appreciate some clarity here. So I really appreciate this question because it does give me a chance to clarify some things that maybe weren't so clear in that video. So what I advocate is genuinely creative. I never propose that students shouldn't solve or construct their own theorems or proofs. And in fact, my Classical Math 1 curriculum is entirely built around that idea that students will read the original works and then they will have the opportunity to creatively solve their own theorems and proofs. And so this is actually dramatically different from what you see in a textbook. In a textbook, you're usually given, like if you're doing a geometric proof, usually you're given a framework around which to build your proof. And you're given lots of examples, and you're basically, there's a lot of hand-holding going on in proofs because most textbooks don't actually teach proofs all that well. And so what I do instead is I give students less hand-holding, but more examples of real proofs. And so they read all these examples of real proofs that Euclid has written, and then they're tasked with the challenge of doing an analogous proof. And so now I say, all right, well, you saw Euclid prove all these things. Here's a different problem. How do you prove this? And I sometimes will tell them, look, there's more than one way to solve this. And in some cases, I've actually introduced, this is kind of a secret, I've actually introduced, I don't want to say errors, but misdirection in the directions. And so the idea is that students will have to exercise creativity if they're genuinely going to solve these things. And so what I mean by misdirection is that there's an early example or early exercise that I give where if you're not thinking extremely precisely, the problem seems pretty straightforward. If you begin to think really precisely, you realize that you can't actually accomplish what I've asked you to do without adding additional language to the problem itself. Because otherwise you run into the problem where you have conflicting definitions and whatnot. So that requires a lot of creativity, I think, on the part of the student. So that's that part. And so I would argue then that traditional math textbooks actually require less creativity on the part of the student because they give you just a bunch of exercises to solve, and there's no real creative activity going on if you're just solving problems using a method that you just memorized, right? There you're just applying a thing that you were handed, and there's less independent thinking going on. So that's what I have to say on that. Secondly, I don't ever recall saying that math shouldn't be considered a mental exercise. It's possible that I've said that. But if I did say anything like that, what I meant was that that's not the primary reason for studying math. In other words, it's kind of like when you tell students, well, one of the things you get out of math is character development because it's hard, and so you should study math because even if you never use it, at least you've built character. That's a terrible reason to study math because the student wants to know, well, aren't there better ways for me to build character rather than working 30 problems, right? And so when I say, if I've said that math shouldn't be considered a mental exercise, I mean, it is mental exercise, right? What I meant was probably that that's not the primary reason we study math is because it's like mental weightlifting. I mean, that's a reason, but that's not the primary reason. And so if we denigrate math to the position of simply being mental weightlifting, I think we've done mathematics a disservice. And we've also done a disservice to our students by turning something which is genuinely supposed to be a pursuit of truth and beauty into something that's a little more than, weightlifting. And that's not to say that there's anything wrong with weightlifting. It's just math is not necessarily just that. The other thing I want to address is in this question, I'll just read the part I'm thinking about. It says, when would students have the opportunity to become critical thinkers and problem solvers and creative with mathematics? Hopefully I've already answered that, but I just also want to point out that critical thinking, all we mean by this is clear, logical thinking, right? And that's exactly what you get from studying math in the way that I've outlined. When you study math in a textbook, there's actually lots of really sloppy thinking that goes on in most textbooks. For instance, I have a geometry textbook from a major textbook publisher, and one of the things that tickles me, as well as frustrates me, is the fact that at the beginning of the book, when they introduce concepts of points, lines, and planes, the book explains in detail what is meant by point, what is meant by line, and what is meant by a plane. And then, immediately after spending 4 paragraphs defining points, lines, and planes, it says, oh, but points, lines, and planes are intuitive concepts and are not defined. And to that I think, well then what did we just spend 4 paragraphs doing? Clearly, whoever wrote this textbook wasn't really thinking in a very precise manner, right? And so stuff like that, right, which you would notice if you've got training in really clear and precise logical thinking, most people don't notice. And there's lots of sloppy thinking, or I should say imprecise thinking, that goes on in textbooks. And that's not to say that textbooks don't have their place. It's just to say that, well, I think we could do better, right? Okay, so I'm hoping that I answered the questions that were in that first question. But if you have more questions, please let me know in the comments, and I'd be happy to make another video like this, or maybe just if it's something I can answer relatively quickly, I'd be happy to jump in the comments and give you some kind of an answer. I'm going to address another question that I get all the time from parents. And I get emails where parents will ask me, what course of study do you recommend to prepare students for classical math? How does one teach lower math classically, right? So as we're teaching younger students, how do we prepare them once they get to high school to do this kind of thing? One of the things we have to understand is that when students are in the lower school, so not high school yet, they're not prepared for primary sources. Once they get the 7th, 8th grade, maybe we can begin to introduce some things, but before then, no. And what we need to do is we need to focus on the basics. And so at the lower levels, there's less of a need to emphasize the why of math. So that level of understanding, answering the why questions, why things work, how they work, is less important than just drilling memorization. Now, that's not to say that you shouldn't answer those questions when students have them. I mean, that's important to answer those questions. But the why becomes more important when students enter the logic stage of development, right? So that's roughly, I think, elementary school. Or junior high. So here's what you need to do then with the younger students to prepare them really to do well in mathematics later. There are 2 points of emphasis. The first one is that you need to emphasize memorization and math facts, or memorization of math facts. So for example, students need to know their multiplication tables. They need to be able to do addition and subtraction and division, right? All these things need to be simple by the time, or I should say simple to the student, by the time they get to high school, certainly. Every now and then I'll have students who haven't memorized their multiplication tables, and they're in high school. And this is a real problem because now they're no longer able to work as efficiently as students who have memorized these things. And it really hampers their ability. So memorization and math facts are very important because these are foundational things that everyone needs to know. And here's the other side of this that you need to emphasize. You need to cultivate wonder, a sense of wonder and curiosity with respect to mathematics. So memorization on the one hand, and then cultivation of wonder and curiosity on the other. Now, how do you cultivate wonder and curiosity? Well, you do this by looking at the mathematical harmony of nature. And so by doing this, you're actually addressing 2 things: the order in mathematics and the beauty of mathematics. And you don't even have to use those terms necessarily, right? Just by looking at the mathematical harmony of nature, there's lots of examples. You could look at how, different things in nature follow the Fibonacci sequence. You could just look at patterns, how mathematically patterned nature is. And in doing this, not only are you emphasizing the order and the beauty of nature, but you're also presenting nature, presenting the natural world as something which is created by God, which is also important, right? And so there you're also showing students, look, mathematics is important. It's a thing which God has made. The world is patterned mathematically, and all this speaks to the miracle that our minds, which are rational, correspond to the world, which is also rational. And there's no reason why these 2 things should correspond, right? Except for the fact that God has made them to correspond so that we can know Him through the things that we see. So that's the other thing, right? So looking for patterns and then guiding students towards their discovery. And these can be not just patterns in nature, but even patterns in numbers. So you could look at the multiplication table, for instance, and ask students, well, what patterns do you see here? There's lots of patterns once you start looking, especially around the squares. So that diagonal line that gives you the squares in the multiplication table, there's lots of bizarre patterns once you start paying attention around that area. So when you do this, you're also emphasizing, again, the rationality of math, so the order of math, and as well as the truth of math, right? Because now there are patterns that we can see. We can see these patterns continue. And in doing all this, when students begin to see that these things are there, it will not only help them cultivate a sense of wonder, but also curiosity, because now they want to know more. What else is there? So I'm going to stop there. I hope that was interesting. Hopefully that was helpful, clearing some things up. And again, I apologize for not making more videos. Lord willing, I'll find a way of balancing everything that I'm doing in such a way that I can make more videos. I'd like to. I have some plans to make some more videos. Please subscribe if that sounds interesting to you. If you feel like these videos are worthwhile, that will give me more encouragement to continue making these. And we'll see you next time. Thanks for watching. Bye.